Welcome! In this video, we're diving into the world of C++ smart pointers. Smart pointers are a crucial tool for modern memory management in C++. They help you avoid memory leaks and dangling pointers, making your code safer and more efficient. We will explore what smart pointers are and how they can be used effectively in your C++ projects. We'll cover the three main types: unique underscore pointer, shared underscore pointer, and weak underscore pointer. Let's get started. Before smart pointers, we had to manage memory manually using raw pointers. This approach is error-prone. For instance, forgetting to deallocate memory leads to memory leaks, gradually consuming system resources. If you delete a pointer but continue to use it, you'll encounter a dangling pointer, leading to unpredictable behavior. Also, raw pointers often have unclear ownership semantics, making it difficult to track which part of the program is responsible for deleting the memory. Exceptions can also cause issues, as a resource might not be deallocated in the presence of an exception. Consider this example. We allocate memory for a resource using the keyword new. If an exception occurs within the doSomething function, the delete PTR line might never be reached. This results in a memory leak. Furthermore, the PTR becomes a dangling pointer whose usage leads to undefined behavior. Smart pointers address these problems by automating memory management, ensuring resources are properly deallocated and preventing common pointer-related errors. Let's begin with unique underscore pointer. This provides exclusive ownership, ensuring only one unique underscore pointer can own a resource at a time. It prevents copying, allowing only moving, that is, transfer of ownership, to maintain exclusivity. Crucially, it offers automatic cleanup. The resource is automatically deleted when the unique underscore pointer goes out of scope, preventing memory leaks. Here's a simple illustration. First, include the memory header. Inside the unique pointer example function, we create a unique underscore pointer to a resource using standard make underscore unique. This ensures proper allocation and exception safety. To use the resource, we can call its methods using the arrow operator similar to raw pointers. When the pointer goes out of scope, no need to worry, cleanup is automatic, ensuring no memory leaks. Now let's delve into common operations with unique underscore pointer. The preferred way to create them is using make underscore unique, which provides exception safety during allocation. Moving ownership is done using standard move. The original pointer then becomes null PTR, signifying it no longer owns the resource. You can access the managed object using the dereference operator. You can also release ownership, obtaining the raw pointer, but be cautious, as you then become responsible for deallocation. Resetting allows the unique underscore pointer to manage a new object, automatically deleting the old one. Consider this code snippet. Here we create a unique underscore pointer using make underscore unique. Then we move its ownership to another unique pointer using standard move. After the move, the original pointer is empty. We can then reset the second pointer with a new object, deleting the previously managed resource. This process ensures proper resource management and prevents memory leaks. Next, we'll explore shared underscore pointer. It offers shared ownership, where multiple shared underscore pointers can own the same resource. It employs reference counting, tracking the number of owners, and deleting the resource when the count reaches 0. The reference count is thread safe, but remember that the pointed object itself might not be. Here's an example. We create a shared underscore pointer using standard make underscore shared. Inside a scope, we create another shared underscore pointer pointing to the same resource. Both pointers share ownership. When the second pointer goes out of scope, the count decrements. Finally, when the first pointer goes out of scope, the count becomes 0, and the resource is deleted. This mechanism ensures resources are deallocated only when no longer needed. Let's examine common operations with shared underscore pointer. Creation is best done using make underscore shared for efficiency and exception safety. Copying shared underscore pointers increases the reference count, Reflecting shared ownership. You can check the reference count using the use_count function. Resetting releases ownership, potentially deleting the resource if no other shared underscore pointers own it. When using shared underscore pointers, it is important to consider performance due to the overhead of reference counting. Let's walk through this code. Here we create a shared pointer using makeShared. We then create another shared pointer by copying the first one. Checking the reference count, we see it outputs 2, indicating 2 shared pointers are pointing to the same resource. Resetting one pointer decrements the count. Thus, the other pointer's use count is 1. This demonstrates how shared underscore pointers manage shared ownership and automatic lifetime. Now let's investigate weak underscore pointer. It provides a non-owning reference, observing a shared underscore pointer without affecting the reference count. It allows expiry checking, verifying if the referenced object still exists. It helps in breaking circular references, preventing memory leaks that could occur with shared underscore pointers alone. Here is the illustration. We create a shared pointer. Then we create a weak pointer observing the shared pointer. To use the weak pointer, we must first lock it to obtain a shared pointer. If the lock succeeds, we can use the temporary shared pointer to access the resource. This ensures we're only working with a valid object and prevents accessing deleted memory. Consider a scenario where object A has a shared underscore pointer to object B, and object B has a shared underscore pointer back to object A. This creates a circular reference. Even if there are no external references to these objects, their reference counts will never reach 0, resulting in a memory leak, since the objects are never deleted. The solution is to use weak underscore pointer. Here we define a node class with a shared pointer next and a weak pointer previous. By using weak underscore pointer for the previous pointer, we break the circular reference. In the createNodes function, we create 2 nodes using standard makeShared. We assign node 1's next to node 2 and node 2's previous to node 1. The assignment to the previous pointer doesn't increase the reference count. When these nodes go out of scope, they are properly deallocated, preventing memory leaks. The image shows a memory leak can occur where 2 objects with shared pointers pointing to each other will never be deleted, even if they are not being used anymore. To solve the problem, use a weak pointer. Let's compare the smart pointers. Unique underscore pointer provides exclusive ownership and is best suited for single-owner resources. Shared underscore pointer offers shared ownership, ideal when multiple owners are needed. Weak underscore pointer provides a non-owning reference and is useful for breaking circular references. Raw pointers are suitable for non-ownership observation, but require manual memory management. Best practices include using unique underscore pointer as the default choice, preferring make underscore unique and make underscore shared over direct new, using shared underscore pointer only when sharing is necessary, and employing weak underscore pointer to break circular references. Pass smart pointers by value to share ownership and raw pointers or references for observation. Avoid using get unless absolutely necessary. By following these guidelines, you can effectively leverage smart pointers to write safer and more efficient C++ code. In summary, unique underscore pointer is for exclusive ownership and automatic cleanup. Shared underscore pointer is for when multiple owners need access to the same resource, and weak underscore pointer is for breaking circular references and observing shared objects. Thank you for watching. For further resources, refer to C++ reference, Effective Modern C++, and C++ Core Guidelines. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.